So there's a ton of demos in this, so I'm gonna try to run through this. But I have to admit, I did something really bad, because I'm kind of like a skeptic on the whole AI thing, and I don't know what got into me, but I put AI in my title. Perhaps I gave in. But this talk is really about building models, right? Like models of everything. The rocket engine, the sensors, the camera system, and trying to do more and more modeling so you have less problems when you actually go into the flight test. So super special thanks to my team, because without those guys, I would not be here presenting this today. So we're gonna run through a bunch of different pieces, and I'll try to tie a common thread in how all this stuff fits together. This has been a really long journey for me. It actually started, I did a CRADA with this guy named John Livingston at Wright-Patt Air Force Base when I was like in my very early 20s when I started my first company. And it was on basically parametric modeling systems for space vehicles. And around 95, I went off into the software side. And then about 5 years ago, I reconnected with John. He retired, and now he's working with me. And we're basically rebuilding that original vision. People call that digital twins, but I like to call it parametric virtual models, mainly because John and I were working on it before this whole digital twins thing started. But and I'll try to explain a little bit about what I mean by that. So before we get started, really special thanks to Dr. David Blewett. He's the principal investigator for the Lunar Vertex Prism lander rover mission that's going to go to the moon next year. We're building, Aclectic's building a digital twin of the region of the moon called Rainier Gamma, the lander, and the rover. And also super special thanks to Michael Katz, Robert Graham, and Patrick Pinchar from AMD for providing all the hardware that we're using to do all the modeling and simulation. So really quickly, I wanted to give it context, right? So the whole CLPS is a series of commercial lunar missions, right? So companies are building the landers and the rovers and whatnot, and NASA's basically taking, they're not designing or doing any of the development work to get the vehicle or whatever the payload is to the moon. They're basically just, they're purchasing a seat, and it's up to the company to build the solution to get it there. The Rainier Gamma mission, this is really kind of interesting, is in this one region of the moon, there's this kind of like this lunar swirl, right? And there's like a magnetic anomaly. Now, what's really kind of fun about this is if you guys remember 2001: A Space Odyssey, there was like this obelisk, and there was a magnetic anomaly. Same region. So maybe Arthur C. Clarke, knew about this stuff way back when he was doing 2001. So the mission is to go study the this lunar swirl and to look at what they think possibly a comet hit that region, maybe, and that might have caused the magnetic anomaly that set the Rainier Gamma. So when I went off into computer graphics in the 90s and got involved in games in the film industry, I did it mainly because I had a vision of building very rapid modeling systems. And, building tools for artists was kind of sort of like, really, I wanted to build tools for myself. So I had to get a lot of background in a bunch of different things that were kind of disconnected, like languages, compilers, runtimes, graphics, rendering, and then, and simulations, and then tie it back together. So when I came back and said, okay, I want to reapply this, the first thing I did was I went back to, my original background was all, aircraft or spacecraft design. So what we did was I picked an area of space rescue, and we did a vehicle design with some of my friends from the old days. And I kind of convinced them on this idea of a rapid response space ambulance. And then so we presented that at 2024 at SciTech. And then after that, we did another follow-on paper on distributed simulations. And then I did another one just recently on a CIS lunar rescue vehicle. So the important thing to understand is that a lot of the graphics that you're going to see in just a minute is based on a lot of thought that went into the design of the vehicle. And I think that's the most important point of the whole presentation. It's not just the graphics. The graphics help, but it's also the physics and the modeling, right? So for Aclectic, those examples, like the CLPS 12 mission and the Ephemeris project that we were doing before, and Marv and all that, they're just an example context for the work that we're doing. So what are we doing? Well, we're building a kind of a very specialized edge supercomputer and a software modeling environment on top of it. And so what we're going to show you is kind of like at the very tip top of it, how we're applying it and then building our way back down. So there's a whole bunch of stuff that we'll walk through, but the hope is that you'll see a common thread. So the use cases, for mission architecture and mission analysis, training astronauts, distributed simulations, and then there's, and I'm also thinking very carefully of, the Artemis III mission is going to come up, and when the Apollo 11 landed on the moon, there was like 600 million people watched it. 600 million people. The largest online game was like 40 million with Fortnite. So you could think what's going through my mind, because Fortnite is where a lot of money is made. So I'm guilty of being an entrepreneur too. So I'm thinking about, so I'm doing all this parametric modeling. Okay, how would I move this stuff so when the Artemis III mission happens, you could actually experience it, train for it, go along for the ride, and be on the moon, and then do something fun after the mission happens worldwide. So that's kind of where my head is. Like, that's what polymath is really all about. So a couple of years back, we put some kind of ideas together for what would be the space flight simulator, like a vision for it, and then we built it. So I'm going to show you really quick a bunch of demos real quick. Hopefully I probably won't burn through all my time here. But this is the first simulator for the Ephemeris vehicle. So what's fun about this is one of the first things I did back in 1989 is I modeled the aerodynamics of a hypersonic wave rider at NASA Ames on the old supercomputers back then. And what we're doing here, this is this kind of a wave rider-like system. It's a two-staged orbit. First stage is a Falcon 9-like rocket, and then the second stage is dual inward turning scramjets. So we modeled everything, the sizing of this thing, all the way down to the rocket engine, the tanks, all of that's published in the paper that I talked about earlier. And then we started looking at landers, and then kind of modeling this. And this was really early stuff. And this was when we started with the Cesium Moon. Cesium Moon came out, and then we just jumped on it. And and we were looking at trying to do, so one of the things that I'll talk about in a little bit is how we upscaled, the resolution, because Cesium Moon is pretty coarse-grained, and we needed it all the way down to, sub-centimeter scale, and I'll talk about that in a little bit. So this is, here you'll see like a heads-up display that we built, and that's all built in Rive. And you can fly this. I could load it in my system and fly it, but so we built a docking simulator. And so some of this was with the Starship HLS, so we modeled that. Now this was fun, is what we're doing here is we took the Blue Moon lander, and then we put a LiDAR system on the bottom of it. So we actually modeled the LiDAR as well. And and there we go. See, it wasn't a RUD, otherwise you guys would have had to clap. Unfortunately, we landed. So anyways, so this is the work that, a lot of this is work that's been done over a long, long time. And this is about trying to build a simulation appliance. So the number of physics simulations we have to do are insane. So whenever you're doing a design process, and you're looking at the entire flight profile of the vehicle, if the vehicle goes in and out of the atmosphere, now you're talking about hypersonic flow. So you're looking at potentially 10,000 simulations of 30 million elements, where each simulation takes about 3 minutes to run. So the point is that most hardware platforms being designed today are not being designed for really HPC-like workloads. They're largely being designed for AI. And AI workloads are largely very narrow. They're very contiguous in memory, right? And they're not as dynamic. So in computational fluid dynamics, in an area that that we do a lot of work in, the workloads are much more irregular and dynamic. So what we're trying to do is build our own accelerator that has an FPGA that sits in front of a conventional GPU or APU-like system. So, and what we want to do is we want to have a super dense system. Now, why do you want to go do that? Well, if you look at modern supercomputers, like the big ones, the exascale machines, you'll find out you're getting close to 3% utilization of the flops. So what they're doing is they're using massive amounts of memory. So if you have an enterprising mind and you want to well, why not build a machine that has more memory in it and utilize more of the flops? Well, how do you do that? Well, in conventional GPUs, you have something called memory coalescing. And memory coalescing is something that there's a unit in a modern NVIDIA GPU called a memory coalescing unit. What Aclectic is trying to do is make that as a programmable engine. So you reorganize your dynamic data structures and your pointers, and you make them more memory contiguous. So when you feed it to a GPU, it tends to be a lot faster. This is important because we have to run 10,000 sims, and we want to do it in 5 days. That's why something like this is so critical. Because most hardware companies, they're fixated on AI. And AI is great for a lot of things, but you're not going to AI your way out of reentry physics. And that's why, if you notice, several of the starships that have crashed because of problems with reentry. And also in Artemis II, there's some issues with respect to the heat shield. So, physics is really important, guys. We can't forget about it when everybody talks about AI. So this is kind of like the architecture we're building for our simulator. It's notional because we're kind of iterating our way towards it. And this is kind of like the software architecture we're building. Not all of this is fully functional and working yet, but parts of it are. And parts of it are almost ready. Like we've been working on the telemetry. So we have all of our systems and subsystems we have modeled, right? And then we're actually feeding that via web sockets, and we're using CCSDS, which is a common payload format for the space sector, and then we're feeding that into Cosmos. And then the idea is we can take so for example, the camera feeds, right, for off the spacecraft, we can pixel stream them to Cosmos, and then pixel stream from there into either a web application with Dart Flutter, or you could use. I purposely didn't want to use OpenMCT, which is we wanted to go with a little more performant protocol, so we went WebSockets and binary packets. That's why OpenMCT uses JSON, and we specifically didn't want to do that. That's why we went to Dart Flutter for the web app. Now, the interesting part is, when we're done with this, the next logical demo that we're going to build is we're going to replace the pixel streams of the camera. Instead of going into the web application, it'll go into Fortnite. So we don't want to use Fortnite graphics. We're going to do full path tracing, but we want to get the scale of Fortnite. So that's something I'm really excited by. And there's a really good reason why. Because I remember what inspired me. When I was in kindergarten, I saw this big book of the Apollo things. And it just set me on my path. And I knew what I wanted to do. So I know there's lots of kids out there. And if we could give them the really photorealistic simulators that actually act like the real thing and are used for training, and then we coordinate that with the real thing, with the real mission, I can't imagine how fun that would be. So I'm actually building this pretty much for me, to be honest with you. Okay, so we built our own CFD engine. The CFD engine was fully parallel top to bottom. We demoed this at NAB 2018, and And then we also built a delta tracking path tracer, right? So this is a volumetric path tracer, and this was also done in 2019. We demoed that. So that one's a ray marcher. So what was interesting about this is it's scaled. And you know, if you look at the NVIDIA plugin for Unreal, 1 GPU. If you look at the Unreal Engine, it's 1 GPU. We're going after, in our prototype system, 16 GPUs, plus the floating point accelerators for the CFD engine. So, and I'll tell you why that's so critical in a second here. So really quickly, this is a little more detail on the Nova C lander, right? And so the interesting part there was the camera module. There's actually 3 modules with 3 cameras apiece. So now, you know, obviously we put cameras on it, we model it all the way down to the lens, and then we're path tracing that. So now you're getting, you know, 9 feeds simultaneously coming out of the spacecraft. So unfortunately, we couldn't get that ready to show here, but we've got something else that I will show. So for the rover side, you know, we also we modeled the lander and the rover, you know, down to the sensors on the rover. And so I'm going to quickly go into some of the techniques we use to get higher resolution than cesium moon. So like I said, cesium moon is like, you know, we wanted to go anywhere on the moon, you know, with the cesium tiles, but we wanted to dynamically update the tiles with higher and higher resolution. And eventually, we want to get down to sub-centimeter scale. Why? Well, because the rover's that big, right? So we need a lot higher resolution than is provided there. And so what we were doing, we were up-resing the tiles. So let me show you how we did that. So we built a prototype pipeline in Houdini, and what we were doing was we were using like essentially NASA elevation maps, right? And then we took that and we were essentially getting 40x resolution from that, right? So we were upscaling that, and so our goal is to take it, and you know, we could take a tile, break it down into subtiles and so on. And then, so the goal is to get it all the way down to sub-centimeter per pixel resolution. And then the other thing we did was we built a whole procedural rock pipeline. So we could start with you know, a volumetric rock, and then we would dynamically generate it, and then we would use Unreal's PCG to populate it, right? Now the next logical step is instead of you know, rendering it there, what you do is you render it and you build a Gaussian splat, and then you do a final path trace or a lighting pass at the very end. So this is what we're working towards on the next go around. This part already runs, and I'll show you examples of that.
Yeah. We have 1 more minute.
Okay, so I'm just almost done. So so this is some volumetrics we were experimenting with just recently, and I'm gonna just show you a couple of quick demos. So this is the rover. The thing about the rover is we're modeling both the camera views. I'm going to run these simultaneously so you could see. So what's interesting here is the top one actually showing LiDAR on the rover. The other one, there's 2 stereo cameras, and then we're modeling the cameras there too. So so this is the, you know, this is important because once it lands, the rover kind of runs away from the plume, and then you essentially need to be in line of sight to the lander. And we needed to model all that because if you're landing somewhere where you weren't supposed to be, then you know, you don't want to go over underneath a ditch or something, then you lose sight to the communication. So all of that, you know, that's all working. And then this is some work we did with path tracing and deferred rendering for that region of the moon using all the techniques we talked about a minute ago. So the issues that, you know, because a lot of this stuff just came out, we're running into issues with being able to leverage nanite in our path tracing, and then we're getting, you know, some things aren't working like they should, but hopefully we'll be able to resolve all that. And then the resolution, so the resolution here isn't mainly because we don't have nanite working yet. There's some issue glitch that we've been trying to work out.
We are running out of time.
Yep,
So
I'm done. So, so these are all the images, and then there's a bunch of references.
Thank you very much. Yeah.